afternoon, everyone. I work in the Industrial Solutions Division. I focus primarily on software strategy, and just recently we've started developing an open source strategy. So I got more involved back in the open source side of things. Little bit of interesting title. I know what it said on the schedule was I'm going to be talking about Akraino and Aleph Edge. So I'll eventually get there, I promise you. But I wanted to kind of just set a tone a little bit around why we're interested in open source from an industrial perspective. Also, I didn't really come up with the terminology. The fourth industrial revolution, is a term that's out there. You've probably heard of the word Industry 4.0. It's actually more of an evolution than a revolution, but I prefer revolution as well because it kind of sort of gives a unique taste to it. I have to show you all that stuff before we get going. Okay, so what is this industrial revolution really all about? And again, just to set some context, when I'm talking about industry here, I'm really talking about manufacturing. So this is industries that manufacture things. And broadly speaking, there's three main areas of manufacturing that we look at. There's process manufacturing. So this is where you basically have a raw material that through a process you convert to some finished good. This is sometimes also called continuous manufacturing. A good example would be oil refining. So you're taking crude in one side, all your tools, all your machines are basically working on that crude as it goes through the process, and what comes out the other side is gasoline, ethanol, methanol, all the byproducts. But that entire process is called process manufacturing, in that case, continuous manufacturing. We also have discrete manufacturing. This really involves taking existing finished products and putting them together in some other configuration to develop another finished product. Good example there is the automotive industry, so a car manufacturer, discrete. And then there are combinations of hybrid, what we call hybrid manufacturing. Pharmaceuticals fits into this primarily, where you might take some finished goods, add a few more processes to it, and then come up with something else. So it's a transformation more than anything else. This industrial revolution actually applies across all of those broad segments within manufacturing. So a good way to think about this is, we've been involved in manufacturing, at least. Automation has been part of the process going back a couple hundred years already. From the time that we really kind of harnessed steam as a way to power machines, we've been involved in this industrial revolution, and it's marched forward up until today. Continues. Probably the biggest trend that really came across manufacturing the way we understand today is electricity. So once we could actually harness electricity and start powering machines electrically, I think that's where we got to mass production of goods. Prior to that, steam gave us some autonomy, some capabilities, especially in obviously in transportation, but also in textiles. But really, electricity was what really drove the manufacturing processes that we still use today forward. So that started 1800s, late 1800s. Obviously, Intel was heavily involved in 1970 in kind of the creation of the microprocessor industry. And that really moved us into what we have today, which are fully automated factories. If you go into some of these oil refineries today, the process is completely automated. There are still many humans involved, but really the automation part of the process really started with microcontrollers. So really that's more of the revolution from electricity was to microcontrollers. And then since then we've been marching along, this trend to move, not so much get humans out of the way, but to create more intelligence in the machines themselves, so that the process defines how the machines operate, instead of a human defining the process, which then selectively the machines. So this definition we have up here for the intelligent factory, which is really the fourth industrial revolution or Industry 4.0, is quite important. The first element I want to call out there is open and fully interoperable systems. Today, for the most part, the machines that control the process and the computers sitting behind those machines are completely proprietary. Systems don't talk to each other. Software doesn't interoperate. Generally speaking, if you're going to bring up a process industry today, if you're going to build a new oil refinery, you'll go to one or two vendors, and they'll supply every tool in that process to you. And it'll be very black box, highly proprietary. This revolution is going to open that up, right? We're going to start software defining most of the elements that make up the process. So for you guys that are, come from the networking world, this is somewhat equivalent to, what happened in the networking world 10 years ago with software-defined networking. We had closed, proprietary, fixed-point, devices that allowed software to open them up, and now we have software-defined network and even, virtualization of network functions. So something similar is what we're seeing happening in the manufacturing industry. Another one really to call it over here is the software-defined process. So again, using software to redefine software. Very important. One of the things we have today, especially in discrete manufacturing, is a lot of robotics. Those robots are still programmed by humans, and the next evolution where this is headed is that robots will program robots. So as the process evolves, as you're building a motor vehicle or refining oil, the system learns about itself and continuously refines that process. So that's where we're headed. Software-defined networking, another very important element. I won't talk about that much today as we kind of get into the open source part of it, but it is a completely accepted part of this revolution is that all of the elements in the factory will become software-defined. Where we're starting today is more at those higher level processes, so comes sort of down at the machine itself, how it interacts with the process and how it talks to the rest of its neighbors, but the software definition of network functions is coming as well. Intrinsic security. So one of the things that, especially on the process side of the industry, is very concerned with, because these tend to be mission-critical factories, is they don't want to change the way they do business today. So while today these systems are very closed, non-interoperable, they are quite secure. What you find from a networking perspective today in an oil refinery is you have an air gap between your process network and your IT network. So these machines are not on the internet. They don't get viruses unless someone goes and actually puts a USB drive in somewhere, like what happened in Iran a couple of years ago. But today, that's kind of sort of how security is handled. As we move to software-defined, the industry, from a standardization perspective, is focusing on intrinsic security. So security is part of the paradigm, is part of that initial software definition. So as a new tool or machine gets built with open networking, open software, intrinsic security is paramount. And then one of the things we've seen a trend that's been growing pretty much since the mid-'80s till now is this idea of machines understanding how to fix themselves. So using analytic tools to look at the information coming from sensors and actuators and perform or at least notify of when maintenance is required. So again, trying to get the humans out of the process and let machines manage machines. So it's a pretty exciting area to be involved in. Again, I've placed us somewhere where we are today. We're probably on about another 20 to 30-year journey before truly intelligent factories exist. I had the great opportunity to talk to one of the senior fellows at Boeing a couple of weeks ago, and he said his idealized intelligent factory is really a 3D printer with a bunch of 3D printers inside of it that are all software defined. So his factory today can be configured to build, a 787, and tomorrow with a few software changes, it'll build, whatever the next one is, a 969, whatever they're going to call it, right? Instead of building a whole new factory to do it, it'll just software define the processes inside the existing factory. That's where this is headed. So a couple more definitions that I want you guys to get familiar with. So in manufacturing, very standardized industry, again, especially process manufacturing, and this ISO 95 standard defines different layers in the manufacturing process. These layers define today fixed device types and fixed functions, but it also gives an idea of where these layers are going to collapse as more software definition comes in. So if you look on the left-hand side over there, I've got those ISO 95 layers tabbed out there. right down at the process layer, where the machine actually creates the process or touches the process itself, what we call layer 0, layer 1. So these today tend to be very fixed function devices. They're the controllers, the sensors, the actuators. Some of these today are relatively dumb still. They don't really have microcontrollers in them. There might be a pneumatic press, basically just operating on air. Over time, these will all shift to be intelligent devices. They will not only have a microcontroller, they will also be connected over a network. Layer 2, layer 3 is where most of your kinds of control functions exist from a human interaction, so where humans interact with the system. So that HMI is a human-machine interface. These tend to be screens, buttons, alarms. Those are what the HMIs present out. Your SCADA is really a kind of a term that came out of the 70s and 80s. It's basically a network for collecting and then analyzing data relative to the process. Again, this is all done after the fact. So SCADA systems today tend to not be real-time. The data is stored in your data historian. Then over time, analytics processes will go and look at that, that time series data, that historical data, and then a human will get involved again, generally a process controller, and go back and they'll reconfigure the process. Yeah, question? So SCADA is supervisory control and data acquisition system, and HMI is human-machine interface. So an HMI today could be a computer screen, or it could be a machine with buttons on, right? Just how a machine interacts with humans. Generally, your gateway functions exist in layer 2, layer 3 as well. So a typical gateway in industrial is something that bridges a network. So this is where you might bridge from a fixed proprietary controller network onto a traditional industrial network. Not much Ethernet found in industry today. It's another part of this fourth industrial revolution, is to bring standard networking technologies all the way down to layer 0. Today, those tend to be highly proprietary. They might run on twisted pair, but they don't carry Ethernet packets. The gateway function is there to basically bridge those proprietary protocols onto standard Ethernet. And then as you get further up, layer 3 and above, is now you're talking more general purpose compute. So you'll be running systems, Linux, find Windows there, and general networking. So Ethernet will be much higher up in the ISA layers. Another interesting aspect, just from an Intel perspective, why we like manufacturing and this revolution is down layer 1, layer 2, a lot of MCUs, microcontrollers, which is not really our business, but also ASICs, custom silicon. We like the idea of general purpose compute. Why? Because as you move to software defined, now you can start doing consolidation of workloads between general purpose compute devices. So you can take what was a fixed function HMI, maybe it was running on a Windows 95 box, by the way, we still see those a lot, and now you move it onto a general purpose compute platform alongside where the process actually runs. So you can see as we move through these software definition, or through the software definition phase, all of those fixed functions now become portable workloads. They can run anywhere in the factory. This real-time bus that we put over there is going to be Ethernet TSN. It's becoming standardized for this industrial revolution. So all of these workloads will now be connected through Ethernet TSN and will run on general purpose compute. So the entire factory now gets software defined, and these workloads can run anywhere. So you could fire up a workload that runs on an edge compute platform right down to the process. That same workload could then get orchestrated higher up the stack if need be, or to another machine running a general purpose compute hardware. So what do we gain out of this, really? So what's the real reason for doing this? So I mentioned that Boeing example again, flexibility. These industries today tend to be very proprietary. It's hard to make changes. Another company we talk to quite a lot is ExxonMobil. A lot of the Exxon refineries, I think they have 35 of them around the world, are roughly 30 to 35 years old, technology inside. They don't change a thing. The machine breaks, they get the same machine put in. The idea of having a flexible software-defined system is highly attractive to them from a total cost of ownership perspective, you can imagine. So end users like Exxon are driving this revolution through. Yep.
TSN brings a lot of requirements
Yep. Okay, so yeah, so the question is, and just make sure I get it correct, the question is that TSN is a pretty heavy stack to bring in, especially down at some of these, lighter devices at the edge. So the question is really, do we think that end-to-end TSN will exist? I think the answer is yes, ultimately will, and I'll tell you why. Especially down in layer 1, layer 2, what defines these layers is not just the function of the device, it's also the criticality of the timeliness of the transaction, timeliness of the process. So we call them time critical, and I'll show you later on when we talk about the open source part of this. The deterministic nature of a process needs to be accounted for in the general purpose compute and the networking elements when you come to software defined. So to get deterministic transfer of data off of a process to the next process requires both time sync, right? So you need to be able to synchronize clocks and then also deterministically move that packet. So today there are proprietary protocols that do it in industrial. So EtherCAT is one of them, right? So it's built on top of Ethernet, but it carries a proprietary packetization protocol. The idea, again, the industry is moving to standardization, and they see TSN and what's happening in IEEE is the right way to go. So I don't know how to fully answer your question. Will it appear everywhere instantaneously? Probably not. It'll be an evolution. But we are seeing some end users, even down at layer 0 now, are requesting standard Ethernet TSN as part of the package on the machine. So that was kind of just setting the scene for you. Sorry, yeah, one more question. Yeah, so the question is, throughout the AX95 stack, is there, let me just make sure I get it right? Is there a defined area where these workloads will run? Is that really your question? Yeah. Yeah, so I'm sorry, I'm not actually hearing. Yeah, AX95, yeah? Raspberry Pi. Yeah, so I know what a Raspberry Pi is. I'm still not sure what the question is. Does Raspberry Pi fit in as a... Yeah, so when I say general purpose compute, I'm talking about both ARM and IA or x86, right? What I'm talking, when I say the transformation is away from fixed function silicon, so move away from an ASIC to something that's more general purpose. So yeah, you will find Raspberry Pis running down at the very edge. Again, so long as they can be deterministic. So if you have a deterministic function in your process, it requires an ingest from a sensor, some process on that data, and then an output to an actuator. And the process defines timeliness within that transaction, or determinism, the way we see it. So that entire transaction from ingest to compute to actuation has to happen in a defined time. Let's just say 32 microseconds. So long as that ARM device can do it, so long as that Raspberry Pi can perform that deterministically every single time, then yeah, you'll find those devices there. So that was just setting the stage for, kind of sort of the real reason for me being here is to talk about, so how does open source apply to all of this? So not much open source today exists down at the manufacturing edge. So it's literally in those layer 0, 1, 2, probably up to 3, you find very little open source today. Certainly no active open source projects exist that can span all of those 3 layers. So part of what we're doing at Intel is we're starting to invest in open source, around, specifically targeting the industrial edge. So I've called it a landscape. It's not inclusive. These are some of the projects and some of the foundations that we're focusing on. And there's some reasons for choosing these, so I'll run through those. Just quickly, what the colors mean. So the green boxes are really highlight, the big open governance foundations. So obviously, Linux Foundation, OpenStack, you guys are familiar with. Eclipse Foundation is another big one in industrial. They tend to be, Eclipse Foundation tends to run much more point projects. They really, implementations of standards that apply in industrial. And then there are a couple more that are interesting that we look at from an Intel perspective for sure, and that's Open Source Robotics Foundation. So again, very focused on robotics. But as robotics becomes less of a fixed function and much more of a general purpose compute paradigm, so that project is very important for us. And then Haystack. Again, what we're talking about here is the combination of compute and data data interoperability at the edge is very important, and that's what Project Haystack provides for us. So I'm going to go through some of these in a little more detail. I'm just going to call out a few projects that I think are interesting that we focus on, and hopefully you guys will find interesting as well. So Starling X is a relatively new project at OpenStack Foundation. This came out of the divestiture, by the way, of Wind River from Intel. So when Intel owned Wind River, they were actually a subsidiary of the group that I work in, the Internet of Things group. They developed an OpenStack-based platform called Titanium. And being more closely aligned with the Internet of Things group and embedded compute especially, one of the standout features of Titanium is that they could take OpenStack, which is generally a multi-node deployment, and bring it down and run it on a single node. So you could actually fire up a single server and run a full OpenStack implementation, or at least the Titanium version of OpenStack, which for industrial we thought was very important. And so we put a bunch of effort into that Titanium product from an industrial perspective. Very low latency, high availability, 6+9s of availability on OpenStack. When we divested, there was a forcing function on Wind River to go and open source all of those patches that they had made to OpenStack. I think there were roughly 1,600 of them, and that's now ended up in the Starling X project. So it is an OpenStack-based infrastructure. Again, focuses really much, very much on the abstraction layers for compute and memory and storage, but then also has the networking components. So they've brought in all of or most of the networking components from LFN and DPDK and other networking components like that, and they provide that abstraction layer as well. So a little forward-looking in terms of where industry's headed from the network abstraction layer. So we like that project again, small nodes, you can run on a single server, can span to multiple nodes, and they've also got a bunch of tooling around moving your nodes between different locations. Kata containers, another interesting one. Yeah, question. So the question is, are there open source hardware initiatives underway? So the only one I'm very familiar with is the RISC-V from a yeah. Yeah. So you're looking more for open source projects that detail around some of the more open functionality I spoke about? Nothing yet. Yeah, nothing I'm aware of yet. Yeah.
When it comes to manufacturing in general,
Yeah.
you need what's called agile manufacturing.
Yep.
You implement it so that the agility is there. Now, when I program a given electrical control machine, a robot, it will be doing something right. If I reprogram it, it can do
Yep.
different, which is you are an agile being. We are all agile beings, but a lot of the robots are not. Yes, that's
Right.
agility.
But it's coming.
Talked about
Right.
for
Yeah.
25, 30 years in my own practice.
Yeah. But it is coming, all right? So again, when I spoke to that guy from Boeing, that fellow, his whole idea is that his future factory is just a 3D printer, right? That'll always reconfigure itself for the next process. So there are some fundamental parts of it that are hardware specific, which you may not be able to change out. But certainly all of the elements that can be software defined will be over time. I'm not listing any of those projects here though, right? Yep.
Another area where all of this cannot be easily implemented is energy generation, energy distribution of variety of energy technologies, as different as solar, wind, to waste to energy, fuel cells, etc. It's not practical to make everything software. There's a lot of the physical layer.
Yep. Interesting, though, a lot of that industry is moving to software defined. So,
I know.
yeah.
You cannot software define a solar farm to become a wind farm, and a solar farm from one type of solar farm to another type of solar. It's physics based.
Yep. Right. So, but within that solar farm, if I just flip back quickly to this slide over here, within that solar farm, if you built it 10 years ago, right, you would have built it according to that IC95 model. So you would have had programmable logic controllers, fixed function devices on each one of those mirrors, right? Today, instead of doing that, you'll find a bunch of workload consolidation going on, right? So now you can buy the mirror, right? And your PLC, your controller for that mirror is now just an application that's going to run on a server, at the back end of the farm, right? So things are changing, but that mirror will always be a mirror, right?
Heavily in the industry,
Yeah.
solar industry, and mirrors are not the only you can discuss
Yeah.
offline. There are many technologies in solar, many in wind, many in waste to energy.
Right. All right, so Kata containers. So the reason I call this one out, again, I've spoken about this time criticality of processing down at the industrial edge, determinism. One of the challenges with cloud native technologies like Docker and general containerization is that the runtimes tend to not be cognizant of time criticality. So, Kubernetes and Docker are great. Just so you know, it takes a couple seconds just to start up a Docker container, even on a Xeon processor. That might not be fast enough if you're in a time-critical, compute, application down at the industrial edge. So Kata containers are actually VMs that can be orchestrated via a standard container runtime. And because they're VMs, they can take advantage of silicon-based acceleration. So on an Intel processor, a Kata container takes advantage of VTX and VTD. So they're actually accelerated containers. So we like those a lot, again, because it gives us the capability of using hardware-based acceleration and the flexibility of cloud-native computing, where you can take any type of workload and put it in a container, in this case, put it in a Kata container, and have it orchestrated or managed like a container, but take advantage of hardware acceleration. Really, really cool project. Aleph Edge, and we'll talk about Aleph Edge in a little more detail later, but this is a new initiative at Linux Foundation where they're starting to now put an umbrella over a number of edge-related projects. So a couple of the big ones I mentioned over there, Ajax Foundry, go into a little more detail on that one. Akraino, which I think you guys are probably a little more familiar with, being in the networking world. Project Eve is another interesting one that's now come under the umbrella. So those are three, kind of big projects. I think there's 5 in total now under Aleph Edge. But it's a kind of an exciting initiative. So for those of you that went, through Linux Foundation doing this with LFN, it's somewhat a hit and miss sometimes. But this one's pretty exciting because I think the industry's quite rallied around the fact that consolidation in open source is happening early and not late, like it did with the networking world. Project Acorn. So again, when you talk about time criticality, deterministic compute at the edge, and the idea of having portable workloads, virtualization is critical for that. Acorn is a lightweight type 1 hypervisor developed specifically and exclusively for the industrial edge. So, real-time operation through the hypervisor is one of the design constraints. It will also enable safety certification. So again, one of the functions at the industrial edge, if you're in a mission-critical operation, you may have safety certification requirements, and Acorn will be able to provide that. If you took another hypervisor, standard Linux hypervisor like KVM, getting it safety certified is quite a challenge. I'll get into more reasons why that is, but But Acorn right now is very lightweight, about 30,000 lines of code. KVM, we're looking at like 10 million lines of code. Safety certifications generally run line by line, and so the incremental cost of certifying KVM would be huge. So one of the benefits of Acorn, lightweight, small number of lines of code, very focused on time criticality. Zephyr is an RTOS. The two of them, we actually like the combination of both of them, and I'll show you some configurations of how you might deploy a combination of Acorn and Zephyr at the edge. So again, if you're thinking about portable workloads in that layer 1, layer 2, layer 3, traditional ISA model, the combination of Acorn and Zephyr can give you that portability of workloads. So it gives the capability of creating virtual machines. And then Zephyr is a scalable RTOS, that can run as well as a safety RTOS. So it can run safety-related workloads. So both of those are important. So these orange ones, some of these projects are open governance. They tend to, I pulled them out separately because they're not part of these big foundations. They're either open governance or they're single company funded. But again, critical projects from an open source perspective as we start targeting software defined at the industrial edge. So I'll go through these ones pretty quickly. You can read some of these. OPC UA is one of these standard protocols, connectivity middlewares for process manufacturing. So there's two major projects there that are important. Rancher Systems, these are the guys behind Rancher OS, have just put out what they call K3S. So it's basically a cut-down version of Kubernetes, which is K8. They say it's 5 times smaller, so K3 versus K8. Again, kind of important. I didn't really call out CNCF. Again, cloud native is going to be very important at the industrial edge, but lightweight and again, cognizant of timeliness is really the big focus. And so while the Kubernetes project may get there, we're looking at the K3S project as well as another potential way to bring Dockers down to the industrial edge. OpenPLC, again, PLC is programmable logic controller. These are generally what were the fixed function devices that sit on top of the machines and act as the controller. So they're running control loops. They're taking in real-time data from the sensors. They connect to the actuators. They're running some mathematical function or process, and then they're going to do an actuation. All of those runtimes today are very machine builder specific. So there's about 20 major machine builders around the world for process and discrete manufacturing. Each one of them has their own PLC runtime. And they'll only run the control loops from that particular manufacturer. OpenPLC is the first real open source PLC runtime. And so a lot of effort for us is going into that project as well. Again, portability of workloads down at the industrial edge is the real driver there. Okay, so those are the kind of bit of a landscape view. I'm going to move on now and talk about how these apply at the edge. Yes?
Are you aware of the effort in the OpenStack Foundation in Edge?
Yes,
Okay.
I am aware of it. I didn't list it here because it's still a bit nascent, but it is important, right? And again, you've got both Starling X and Kata containers sitting there as both very edge-focused. So yeah, very aware of it. So in terms of how these deployments look at the edge from a software perspective, again, so this is not really ISO 95 based, although you can think of those different layers, kind of sort of the higher layers will be on the right, and then the lower layers in the ISO 95 stack will be down towards the left over there. What I brought in over here is just an idea of what this timeliness really means. So when I talk about time criticality, in terms of the operation that needs to happen in, kind of sort of in that segment of the software stack. So you can see down at the very edge, you're talking, single-digit milliseconds in terms of ingesting data, processing data, moving data. So from one process to another, we've seen cycle times as low as 32 microseconds requirements. Generally speaking, you're in the low milliseconds, though, low single-digit milliseconds. So still, very critical from a timeliness perspective. As you get to the network edge, you're still, probably in the, high milliseconds, low seconds in terms of latency. So the applicability of existing cloud technologies applies much more at the network edge than it will down, at the thing itself. So as these technologies span down, we have to think about them differently. And you'll see as we look at what the software stack provides, you move from infrastructure as a service, right, which generally doesn't really have timeliness attached to it, down to platform as a service. And the platform as a service is going to expose the time criticality needed for that particular function. So a slight difference in terms of how you look at the software stacks, the necessity of the software stacks as you move down. A couple other things to call out. You'll see as you get further down, these fixed function devices will now become as a service devices, so you'll be able to expose networking as a service or gateway as a service. Data management, data ingestion, data management is an intrinsic part of processing down at the industrial edge. The ability to move data in, so now we're talking data plane, not control plane. Move data in, manage it, analyze it, store it. Those are all going to be exposed as services down at the industrial edge. And then finally, control, the actual function of control itself, the function of a PLC will now move to a service. So you'll be able to deploy a software stack, and I'll show you, a bit of an architecture behind one. We'll actually expose the control function itself as a service. Very nice as you think about, the continuum from cloud to edge again. The big cloud service providers today are rapidly moving down to the network edge. Again, what do they provide? Primarily infrastructure as a service. But they're anxious to get down, further to where the data really resides. And so, providing those connectors and these platform as a service capabilities to the CSPs is critical as this industry scales. So what we'll do is we'll overlay some of these projects on them, and you'll see where they play. So Starling X, again, borrows heavily from cloud technologies, so OpenStack, Kubernetes, brings that down. It plays at the network edge, for sure, so it provides all of the necessary network functionality for abstracting network and infrastructure as a service. And also plays, again, because it can run down at a single node, and it has high availability and low latency built into the stack, it can also run down at their private cloud server. So that's really layer 3 in the ISA stack is where Starling X will play. Acorn, again, this type 1 hypervisor, doesn't borrow anything from cloud technologies. It's purpose-built for the industrial edge, very focused on right down, layer 1, layer 2 portability of workloads, also a little bit in layer 3 and layer 4 as well, so you can have consistency perhaps. But very focused, again, down those very time-critical areas of the stack. Type 1 hypervisor, yeah. So it'll be based on a Linux kernel. Yeah. So a very lightweight kernel, and then it fires up, the virtualization environment. I've got more detail on Acorn in a second. I'll show you some. Yeah.
Excellent slides. Just want to make sure I mentioned. Excellent.
Oh, thank you.
Yeah, very well organized and all that.
Thank you.
In the cloud, you probably want to add what's called multi-cloud management. Now that becomes flexibility. If for the user to
Yep.
be able to go to any cloud, any of the services they can pick and choose through a open portal. There are for 15 companies who are in it, but I'm not saying they're dominant.
Yeah. Very good point. So, I didn't, this is meant to be pretty high level. Yeah, there's a difference between the manageability functions from the cloud and, and the data functions. Manageability will always leverage cloud technologies for sure. There's no doubt about that. So Ajax Foundry is another one that we like to talk about for the industrial edge. Again, it borrows from existing cloud technologies, so it's basically a microservices framework. And it's really targeted at that network appliance layer, is where it starts. So it doesn't really have any of the infrastructure abstractions. It really applies around data management, data abstraction, and then can actually apply all the way down to the time-critical layers at the far edge. And then the final one is Akraino. So this is an integration project at Linux Foundation under LF Edge, and it applies all the way through. Right? So there'll be blueprints at Akraino that target every one of these types of software stacks, whether it's exposing infrastructure or services at the edge. And again, it borrows heavily from existing cloud technologies to bring those down either to the network edge or the industrial edge.
One more.
Yeah.
Again, in the edge compute probably, you want to show not only software-defined network, software-defined storage, software-defined
Everything, yeah.
Right? And
Yep.
it's called software defined infrastructure.
Exactly, SDI, yeah. In fact, internally in my group, the group I'm in, we call ourselves SDIS, Software Defined Industrial Systems. Yep. So, exactly, yes. That second slide I showed, all those portable, functions, everything is going to be ultimately software defined. No doubt. So I just called out these four. I mean, obviously there's many more projects, but these are just a couple, just to kind of show you how they vary as you take them down to the edge. All right, so LF Edge, just for those that aren't familiar with LF Edge, again, it's an umbrella project. I think it was just announced in January this year, so relatively new. It's got some, big anchor projects in there. So Ajax Foundry has been going for a couple of years, Akraino just over a year. So those form kind of the anchors behind LF Edge as the primary projects. And then there are a couple more that are in, this is from the Linux Foundation announcement. So EVE, so it's a lightweight virtualization environment for Edge, primarily focused on what we call brownfield deployments. So, it's fine to have, a brand new factory. If Exxon's going to build a new refinery, it's fine for them to go and spend, $20 billion in a brand new factory and software defined beginning to end. That's not how it's really going to work, though. For the most part, you'll be software defining over time. And so EVE allows you to take existing workloads and quickly virtualize them without having to worry too much about, other infrastructure around there. There's a home edge project, so that's focused really around consumer IoT. And then there's Glossary, which is an interesting one. It's basically like an encyclopedia for edge compute terminology. So just a way to standardize on the terminology for the edge. I can tell you just anecdotally, in my group, we probably spent about a year trying to define what the edge really is. Because it's a little amorphous. And if you're in Intel, we have networking guys that'll say, well, the network is the edge. And then you have us guys in the Internet of Things group, well, the thing is the edge. And the real edge is somewhere in between all of that, right? And so this Glossary project is there to help, make sure we can standardize on terminology. So it's open source, so it's really just a group of terms, but important nonetheless. And I think there are 3 or 4 more projects that are about to be graduated now into LF Edge. So it's definitely going to include a number of new projects this year and probably more over time. So functionally, what is LF Edge focused on? Again, this is the launch. So this is back in January. Things have shifted a little bit since then. You can see they're a little more granular in terms of how they define these different areas at the edge. I rolled it up a little bit. So CraneO really starts at the telco edge, the network edge, and kind of sort of moves its way down through the industrial edge. And I'll show you some of the blueprints that are interesting there. EVE, again, much more focused at that industrial edge. Home obviously is focused more for consumer. And then with a couple at the edge there, you see Zephyr mentioned there, Acorns mentioned there. Those projects are not yet part of LF Edge. So we think over time, LF Edge will incorporate them, as they gain more momentum. But certainly, at least from an Intel perspective, our goal is that LF Edge encompasses every one of these deployment scenarios at the edge. Important aspect to call out over here, what LF Edge is trying to do is to make sure that we don't duplicate efforts amongst projects and leverage where we can. So for instance, Ajax Foundry has a defined microservice API, essentially around data. So instead of a blueprint or a CraneO project itself defining another microservice API for data at the edge, they will reuse what Ajax Foundry has already. So that's part of what the LF Edge is trying to establish. A little more detail on Ajax Foundry. Like I said, this is a microservices framework, essentially focused on data at the edge, data management. It's a critical function at the edge. One of the problems today in IoT, and especially industrial IoT, is access to data. It's very difficult to get the data. These are fixed function devices. They're closed. A lot of PLCs we see out there today don't even have a northbound connection. You can't actually get the data out. What Ajax Foundry defines is a microservices API and a plugin architecture to connect to these southbound devices. It incorporates plugins for multiple industrial protocols and allows you to bring in the data, normalize it, so create a single data stream out of all of that fragmented data, perhaps put your own data model around it. So now the rest of your IT can talk to that data. Then it exposes it over standard web service API. So critical function in industrial, this project is about 2 years old. It is commercial already, so there are commercial deployments of Ajax Foundry. Some very big commercialization partners, productization partners have now stepped up to support Ajax Foundry. Canonical, SUSE, Red Hat, all these guys are going to actually deploy, well, they'll include the Ajax Foundry set of containers in their distros going forward. So very big news for the industrial open source community. Ajax Foundry today is really focused again at that gateway function. So again, time criticality is not really part of what they do. They've really focused around bringing the data in and managing the data. However, they do have aspirations in Ajax Foundry to get down to that industrial edge. So they'll start looking more at technologies like Zephyr and Acorn to bring them the capabilities of bringing the portable workload, whether it's a connector or the data management framework, down to that real-time part of the industrial edge. Not there today, but it is aspirational. All right, so a little more on Acorn. So we've spoken a little bit about this. Again, the things that are important here, very small footprint. So I think this slide is about 2 months old now, 2-3 months old. So there might be around 30,000 lines of code now. They keep adding a little more functionality. But the comparison over here, I think that 290,000 line of code that I mentioned there, that's actually the Zen hypervisor, right? So that's the other open source type 1 hypervisor. And so the differential there is about 5-6x, right? And again, if you're going to take this to safety certification, that differential in the number of lines of code is critical. Acorn has already achieved MISRA-C certification, which is a precursor to safety certification for industrial systems and automotive systems. That MISRA-C certification basically certifies that the development methodology in the open source complies with safety certification rules. So how they develop code, how they track the code, how they fix bugs, how they report bugs, all of that is now MISRA-C compliant in the open source. First time a project's ever attained that. So actually both Acorn and Zephyr, that RTOS, both got their MISRA-C ratings. So really important. It's a pretty adaptable hypervisor, very flexible. One of the reasons we like it so much for industrial is, you can run as a standard hypervisor. So you can basically, you can partition it, or you can have all of your devices, shared through the VMs. So standard deployment mechanisms, for VMs can be leveraged. But the one that we really like when you have mixed criticality in your edge compute, so if you've got workloads that potentially require a safety channel or at least need to be quality managed, you can now run Zephyr in what we call hybrid mode, where you can have mixed criticality in terms of what devices have access to your I/O and when they have access to it, and how you configure your VMs. You'll notice over here we call out both Windows and Android as supported VMs. This hypervisor, this Acorn hypervisor, is going to be commercially available this year in the automotive industry. So one of the primary automotive OEMs in China is going to productize and support Acorn as part of their standard software offering. And obviously Windows is important for industrial. So again, down at that industrial edge, there's a very large installed base of Windows, primarily on that HMI function, so that human machine interface. If it's graphical, generally it's running Windows, old Windows, 95, XP, you see a lot of XP. We say Windows 10 over there. I don't see much Windows 10 in industrial yet, but Acorn will support a Windows 10 VM. So very flexible in terms of how you can configure Acorn, which again, why we like it, especially in industrial where you have these mixed criticality workloads. And again, timeliness of transactions. So the ability to act in real time, to be able to pull off I/O, very short cycle time, be able to push it to compute, whether it's in a VM or in your privileged VM. Very important. And then a little bit about Akraino. So Akraino is an integration project, primarily. I think there's 1 or 2 sub-projects in Akraino that are focused on code contribution primarily. But for the most part, Akraino is looking at various upstreams and pulling those into a project, what they call a blueprint, that target various use cases. We think Akraino is going to be substantial in Aleph Edge. Today it is the only integration project focused at Edge in general. But for us, this ability to pull in upstreams into blueprints that are validated and certified in the open source against commercially available hardware, we think is really primed for Aleph Edge to scale. So from an Intel perspective, we are invested in this. I think this information here is a little old. It says 8 families and 19 blueprints. I think we're up to 11. I see Tina in the audience now. I think there's 11 families and like 23 or 24 blueprints. Yeah. So it's increased a little bit since this slide was created. But a lot of focus right now on Akraino. They're just approaching their release 1, which is coming, I think, now this month. So a number of those blueprints will actually graduate as full release candidates, which means, again, they are fully validated stacks, mostly from upstreams, pulled together to target specific use cases. A lot of the blueprints today are skewed towards networking, so they're looking at that network edge, so infrastructure as a service is what they primarily provide. However, we at Intel, we sponsored a blueprint that we call time-critical edge compute. So again, it's taking a view of that entire continuum at the edge. So while exposing infrastructure is great, we want to expose platform primarily, and in this particular one, we want to expose control as a service down at the industrial edge. So I'll go back to that slide of mine and kind of sort of show you again, where we focus this particular blueprint. So it's focused right down to that industrial edge. Again, time criticality is really important. So we're looking at single-digit milliseconds for the ability to ingest data, process the data, and then perform an action on the data. So very, very fast cycle times. It could also run a virtualized stack. In fact, what I'm going to show you is an architecture that runs virtualized. It'll run Acorn as a hypervisor, so you can have portable workloads as well. So you could do a consolidation function off of the stack as well. So use cases we see, kind of sort of broadly across the industrial IoT. We pretty much focused on manufacturing, so running a soft PLC or virtualized PLC. It also applies in smart buildings. So building controllers do have time-critical functionality in them. And then we also see the stack as applicable a little bit further up, further towards the middle of those deployment scenarios where it could just be a gateway function as well. We see Ethernet TSN as one of the primary enablers for this particular stack. So again, time criticality on the networking as well as the compute layer. And definitely the capability of leveraging Acorn and Zephyr to provide safety certifiable software stacks. Very important. We also see this particular stack as a landing zone for 5G, especially URLLC. So very up-leveled view of an architecture stack. So you can see again, we bring in Ethernet TSN and URLLC as potential networking components. Acorn, bare metal hypervisor, right? So it'll run bare metal in this case. It can spawn up Zephyr as a safety OS if you have safety and time-critical workloads. And then other functions that we see variously depending on the actual workload that we see coming through there. DPDK. So again, if you've got if you're bringing in 5G over here, having DPDK, we think would be important. There's that OPC UA middleware. So again, I showed you that Osado project is something very important. So it's basically the capability of having this pub sub architecture framework that runs on top of your virtualized hardware. And then right at the top of there, this is where OpenPLC would run. So again, bringing in that open source project to software define your programmable logic controllers. So this is a blueprint we put out a couple months ago. We've got today, I think I've got the list over here. All workloads, again, sample workloads. We do think that you could do inferencing on the stack. So one of, when I started the conversation, we spoke about that intelligent factory. One of the elements of intelligence in a factory is the capability of taking the data and making informed decisions in real time. So having an inference engine running right next to your process would be important. So we do see those as workloads that are applicable, and obviously Ajax Foundry could be another workload on top of this. So software contributions today, Intel, we've got IoTech is an ISV, an industrial ISV that signed up, Huawei, and Wipro are all members of this blueprint right now. If you go and look, not much action. We've just got the CI set up. We think we'll be part of Release 2, which is targeted for October. So Release 2, you'll see this blueprint will make part of CraneO Release 2. Functionally, we'll be looking for additional software contributors to bring in workloads, what type of workloads I'd like to run on this base infrastructure. So PLC is one of them, plenty of other real-time workloads that can run on here. All right, so hopefully you found the talk around Industry 4.0, the Industrial Revolution, a little different and exciting. And certainly, we think that the consolidation that's happening at Aleph Edge is fundamental for the industrial revolution to happen, for this fourth industrial revolution to happen. So as Intel, we're very excited about what's happening at Aleph Edge. And certainly, if you guys have any interest in time criticality, processing down to industrial edge, come join us in that blueprint. Yeah. Yes. Yes, so the only reason we mention the line of codes is for the safety certification capability. So today, actually, there are implementations of KVM and Zen that are certified for safety. It's just very expensive. Yeah, so there's an IEEE standard called SIL, Safety, I forget the acronym. But if you look, there's ASIL, which applies to the automotive industry, then SIL for industrial. And there's different layers depending on how many humans can get injured along the way. But what we target in industrial is SIL layer 3 and above, which is a very hard certification to get, and it is from a software perspective, and it does come down to how many lines of code you have. So the fewer lines of code, the lesser costs, the higher the possibility of actually getting through certification. Yes?
Excellent presentation again. There are some items that you missed because of too many things to do.
Yeah, right.
You talked about safety, security, etc. Not in detail, but you
Right.
mentioned it. What is more important is resilience, system resilience at various levels, that even when the criticalities happen, depending on failure modes and what are the criticality levels, it should be able to accommodate itself.
Exactly.
When it is to run,
Yep.
not just say there is a safety issue.
Yep. It's exactly right. It's one of the challenges when you go to software defined. Today, most of the resiliency or redundancy comes from just putting additional hardware in place, right? As we think about software defined or portable workloads, the software orchestration function becomes that critical vector, right? How do you determine that a workload needs to be reorchestrated in a time-critical fashion, and then go to the repository, get the workload, and reorchestrate it? Very difficult problem to solve. Yep, exactly right. Good point.
Is there a conference coming up on these topics that you refer to, and anything part of it full time?
Yeah, so if you want more details in terms of what's going on in process manufacturing, there is a standards body called Open Process Automation Forum.
Okay.
So it's under the Open Group is the standards body, and there's a forum there called Open Process Automation Forum. They just, I think in January, released their version 1 of their new specification for Industry 4.0. I encourage you to go look at that. And you can get involved if you see areas that they're focusing on where you have experience, you should go get involved.
Is there a military version to this?
Military?
A version to this of everything. This is not military as such,
Yeah.
right? And it's standard 480 type of
Yep.
standards to be met. Now expanded into these areas. Is there any work being done?
The answer is yes, but out of my domain. All right. Yep.
A newbie question, I apologize, but Ethernet,
TSN.
yes,
Yes.
what is this stand?
Time-sensitive networking.
And I'm just time stamping the Ethernet?
No, it's actually scheduling. It's timestamping and scheduling. So there's I'll get it wrong. I want to say there's like 11 or 12 different IEEE specs that together make up the Ethernet TSN. So there's time synchronization for sure between the nodes. Then there's also scheduling of the packets on the actual net itself. And then there's bridging that has to happen, right, between different nodes. So lots of different IEEE specs come into it, but the combination is what we call TSN networking. It is, yeah. So PTP is the time sync part of it, correct? All right, one more question, and I think my time's up here. Between TSN and industrial Ethernet? Yeah, so I don't know what industrial Ethernet is. There are lots of industrial protocols that run on Ethernet that have time criticality in them, but they're very proprietary, right? They can't interoperate with IT systems. So the whole idea behind Ethernet TSN is that it's standard Ethernet, so it can talk on a standard, gigabit or 3 gigabit connection, but they can also do the time synchronization and the packet scheduling. So the whole idea, one of the things I didn't mention over here is this revolution is bringing IT into the OT environment. So I remember I said there's an air gap traditionally where the two networks don't talk to each other. Protocols are completely different. So as we start software defining this operational environment, so more IT technologies are coming in, like standard Ethernet.